Yes, good evening, everyone. Welcome to the free aspect webinar series. So this is the fourth webinar series. So today's topic will be the battery and the EV fire safety and resilience. So today we had a very great pleasure to have two very famous speakers in our community. The first is Dr. Wang from FM Global Insurance Company from the United States. The second speaker is Professor Xuning Feng from Tsinghua University. So first of all, I'd like to use this chance to remind you a few things. First, the submission deadline of the 15th Asian Pacific Conference on Combustion will be extended from December 1st to December 10th. So whoever needed more time to prepare the paper, please use this chance to finish your paper and polish your paper. And the other deadline will not be changed. Another thing I'd like to share is next year, we are organizing the fourth International Symposium on lithium battery fire safety, and it will be held in Hong Kong. So if you are interested in the battery fire topic, please submit your papers to our conference. So let me start to introduce our first speaker, Dr. Wang. Dr. Wang is Staff Vice President of FM Global, one of the leading insurance company in the world, and he is a manager of Fire Dynamics Group in the research division. He oversees the research activities focused on battery fire safety, material flammability, and CFD modeling for the fire phenomenon. And his research team recently conducted a lot of experiments on the battery cell module system to quantify the thermal runaway and the fire hazard. And he also developed a very advanced numerical model. So Dr. Wang serves many roles in the international combustion and the fire community. For example, he is an editorial board member of Fire Safety Journal, Fire Technology, and Fire Material. He also chairs the fire research column of the International Symposium for Fire Safety Science. And he is also, I remember, is one of the co-chair of the Combustion Institute of the past symposiums. So let's welcome Dr. Wang to give the first talk. You're muted, it seems.
Let me think.
Yeah, good now.
Can you hear me now?
Yes.
Okay, good. You can see my slides, right?
Right.
Okay, sounds good. All right. Thank you, Xinyan, for your nice introduction, and also thank you for the organizers who extended the invitation to me. Today, I'm going to talk about our experimental work and modeling work for battery energy storage system, BESS. I want to first acknowledge my co-authors, Dr. Dong Zheng, who is our principal scientist leading a lot of effort presenting this work along with a team of scientists at FM. All right. And just to start, I want to give a brief introduction of who we are. The legal name of our company called Factory Mutual Insurance Company, and recently changed to FM from FM Global at a trade name. So this is our largest commercial insurance company, established in 1835 with about 190 years of history for loss prevention, research, and engineering. And the picture you show on the right-hand side is our research campus at Rhode Island, including world's largest fire technology lab, showing on the left, which is our large burn lab. Okay. I'm sitting in the fire hazard and protection research area, which is one of the 4 areas of research, including natural hazard, climate, as well as equipment risk and reliability. So the kind of problem we are dealing with are just showing these pictures, a lot of warehouses, manufacturer space with different material and different storage configuration. So we need to figure out how big the fire will be if there's an incident and how to adequately protect those facilities. So why we do research on battery? It's a very simple answer is because we insure a lot of more and more facilities with battery. And for example, we insure a lot of outdoor BESS system, which is for renewable energy industry. And also we insure a lot of battery manufacturers and car manufacturers who store and manufacture the battery cells, racks, in a very high warehouse facilities. We also insure a lot of hyperscale data centers where currently lithium-ion battery is also populated in the computer racks at a BBU, battery backup unit. And also there's a traditional UPS rooms and disrupted power supplies. So UPS is basically a BESS system installed indoor, which have its own different hazard scenarios. Okay. The facility we insure usually have a stationary system. It's not a car. There's usually the failure mode is initiated either by a thermal abuse or electrical abuse, overcharge, over discharge, things like that. And however, as soon as a fire incident initiated, the fire growth is really due to thermal runaway propagation. So it's all subsequent, cells and batteries are really undergo thermal abuse. So that's our research focus. Okay. We actually have a lot of experience of a similar system of a solid fuel configuration. The difference is the battery serves as a solid fuel, however, is also giving have its own thermal runaway reactions or exothermic reactions and produce a lot of energy within the solid phase. Okay. Just look at how we typically solve a problem of a typical solid fuel, like a plastic, bin warehouse in the automatic storage systems. So we do have different tools. One tool is large-scale fire testing, just reproduce what's happening in our reinsured facility and figure out a worst-case scenario ignition location, just looking at how big the fire develops and using that to guide our hazard evaluation and protection design. We also develop models to model these fuels to capture the key physics, for example, the melting, dripping, the heat transfer geometry change of those kind of fuels, whatever is important to predict the fire development need to be built in the model. However, also model requires fundamental fuel flammability properties as the input data, so that we also conduct a small-scale bench-scale testing to understand how flammability of the fuel, and also using the modeling to link with small-scale bench-scale testing to predict large-scale behavior. Okay. So this is our typical result for modeling for warehouse configuration of certain fuels. You can see the fire development, and you have a sealing plume, activate sprinklers, and there's a water dribbling down and put out fire, and the complex interaction between fire, heat transfer, solid fuel, and liquid phase, thermal radiation, all coupled in the tool. So we can do a lot of validation at different scales, and also use it for engineering, problem solving, and design of the protections. So we're trying to apply similar research tools and methodology to battery systems. Basically, we have a room full of racks. Then we can conduct a large-scale testing of the racks. This is a typical heat release rate that we conducted as a function of time. So this kind of large-scale testing gave us a lot of information, the fire growth, peak heat release rate, and also flame size, and heat transfer to a neighboring target. So we can use that to do a lot of calculation. However, it does have its limitations. Basically the large-scale testing usually only apply to the specific condition that we conduct test for. So we will see a lot of scenarios. We say the battery cells change, the chemistry change, the form factor different, and the module design, the rack design, everything changed, even the room configuration. The question to us, how the fire hazard changed. Do we need to worry about it, or the hazards remain the same? So this is really an open question. We do need predictive tools to solve that problem instead of doing all large-scale fire testing. Okay. So our research approach is to scale down a little bit, starting from cell level, experiment, and also go up to the multi-cell level, module level, and all the way to rack level, so that we could understand the physical insight and building the key physics into the CFD model, and also to extract the cell level flammability data as an input for the model to predict large scale. That's our methodology. One example is a BSS rack with a port cell NMC. Each port cell is about 63 amp hour. You can see in this rack, I hope you can see my mouse. In this rack, it's populated with 17 modules. On the front, there's a little bit of plastic in there. For each module, there's a metal casing. Within metal casing, you can see there's 42 cells grouped in 7 arrays. Each array has its own plastic scaffolding to hold the battery in place. So within this module, there's 7 this kind of arrays, and within each module, each individual cells is in this port cell rectangular. Very thin, but pretty long, and all the cells are just populated in one direction, laterally. Okay. We first show some single cell test. It's a very typical experiment for the thermal abuse. You have a heater, heated the cell in one side. The outside typically is insulation or some kind of heat sink. So after heating a certain time, you're getting venting and thermal runaway, and there's a self-ignition, and the whole thermal runaway and burning only lasts about 20 seconds. So it's a very violent kind of a jet flame and fast heat propagation and heat generation. And this is typical result we are getting. So this brown curve is the heater temperature. So you can see the heater is heating the cell. The red is the cell temperature on the heater side, and also the blue curve is the temperature on the other side of the battery. You can see, the temperature signal of the cell is followed very closely with the heater. At some point, you can see there's a venting and causing some temperature dip. At a certain temperature, you initiate somewhere on the way, the temperature of the cell will rise very sharply. However, because of the heat sink effect of the heater, so it's a big piece of copper metal, so there's some cooling effect. However, on the other side, where you have a better insulation, the temperature rise up much higher to 800 degrees. Another thing you can see, everything happens very quickly. Within about 15 to 20 seconds. There is the temperature gradient at a time of thermal runaway at the beginning, at each side of the battery. The heater side is about 250 degrees at the initiation, and actually at the other side is only moderately heated, about like 30 to 50 degrees higher. Okay. And And really the question is what happens when the battery is going through a different heating experience, right? So we're just subjected the battery cell to different heating rate. You can see as soon as the battery getting somewhere on the way, the behavior is very similar. So the peak temperature is similar. The time of propagation is close, speed up a little bit with reduction of heating rate. However, it's still very similar up to experimental uncertainty. And also the temperature gradient within the cell are similar. So really the big difference is the ignition time, which is subject to different heating condition. So the observation is actually very helpful to build the models. So we need to capture the heating condition very effectively, and we need to track the fundamental properties of, for example, the thermal runaway initiation temperature and heat release rate. Okay, this is a model we built. We actually built a 3 surrogate reaction rate, electrolyte to gas, anode and cathode to some solid and gaseous material, and we're using the experimental data to optimize and inform the kinetic parameters and the physical parameters, for example, heat conductivity and heat capacity, for example. Then we can reproduce roughly the behavior of the thermal runaway at a different heating rate. Okay, and then next step we are going up scale or one more. So we now conduct experiment with multiple cells without the plastic scaffolding, just for simplicity. It's idealized condition. However, we can understand some of the behavior. So I'm going to skip the video for the sake of time. I'll look at some of temperature signal. As you can see, there's a certain self-similarity of each cell's temperature like a signal. The only main difference is when each cell is getting thermal runaway. As you can see, this is a heater temperature. When first cell getting thermal runaway, and all the subsequent cell is still very cold. So the heat conduction is not as effective. So there's a very sharp heat wave is propagating after thermal runaway, but the preheating condition is very limited to the near neighbor of the initial heater and the initial thermal runaway cells. All right. So we basically apply the same model that we developed from a single cell chemistry. Then we figure out what the heat transfer between each cell, so the heat conduction resistance, so that we can predict the propagation and of the thermal runaway propagation between cells. Okay, then we scale up one more and adding more complexity. Here we have 3 modules in this multi-module experiment. As I mentioned, each module can populate in 42 cells. Because for certain simplification, we only populated 12 cells for this set of experiments, so that we can instrument each cell very extensively. So the rest of the module we are filled with insulation. So we have a heater on the lower module on the back. So we are hoping to see the propagation of thermal runaway to this side and trying to see how it's going to propagating to the target module, right? So as I mentioned, now we're only populating 2 arrays, totally 12 cells in this module. And we have a heater here and the insulation, and we can looking at the propagation of thermal runaway. All right, this is the video. I'm not going to show the full video. Basically, you're going to see certain cycles of burning, jet flame, change to diffusion flame, then change to jet flame. Again, this is going to be reflecting the heat release rate history also. But I'm going to show you a little bit more what's going on inside of the module. Here we look at the temperature, time history of profile. This is the heater. This is the first cell. You can see the first cell is getting thermal runaway, and all other cells are still very cold, very cool. even though it's in the same container. So the propagation is very sharp front. However, at later time, the flame actually initiating the cells on the left, and on the target module, the propagation is only one directional from the right-hand side to the left-hand side. However, in the initiation module, you might observe you actually have a two directional propagation, both from the back and from the front. Okay. This is temperature curves, which also shows the physics I'm just described. So at the beginning, the propagation is from the back to the left, is a relatively slow propagation, but at a later time, because you have a both direction propagation, the propagation is accelerated. For the target module, because it's been preheated by the conduction through modules and preheated by the flame, so the initial temperature of the cell is in a little bit elevated temperature. So it's actually accelerated the propagation rate compared to the module of origin. But the acceleration is only moderate, it's not significantly changed. Okay, look at the heat release rate. So the peak heat release rate going to about 100 kilowatt, and you see a lot of peaks and valleys. So each peak is corresponding to a thermal runaway of one cell. You can see there's still a relatively semi-steady state kind of propagation with some level of speed up. You can see the picture, there's a lot of plastic around the cells. And actually at the end of the burning, all the plastic is burned. So basically the plastic is contributing 2/3 of the heat release rate. So I think I need to speed up a little bit. I'm going to just quickly introduce our rack level experiment where we populating this rack only the 5 tiers. So the total energy is equal to the battery within the Tesla Model 3, all right? So I'm going to show the video very quickly. As I mentioned, we actually initiate the thermal runaway at the back of the module number 3. We want to see how this propagation of thermal runaway happens in module and also spreading to modules above and modules below. All right. Now you can see, this time the heat release rate around 100 kilowatt is more corresponding to propagation within the module of origin. And later on, you can see flame getting bigger, the module above getting involved, the fire size significantly increasing all the way to about 2 megawatts. And really the question is, we need to do the prediction, what if we're populating 17 modules, what the heat release rate would be. And that's one of our target to predict, okay? And you can see huge jet flame at a later time. I don't have time to go all the details, but for this experiment, we actually putting thermocouples not in each cell, but also actually in each of the 6-cell array. So we're getting this signal. I want to show what's going on with the propagation. For each cell, it's 6 cells. Yeah, each tile is 6 cells array. The initiation of thermal runaway is right here. You can see it's going to see a propagation in this direction, but also because of flame, you will see some, at some point, the cells on the front side getting initiated almost simultaneously. So initial propagation is relatively slow, about 300 seconds per array. Now you can see here, in the upper region, you're already getting initiated, and then you're expecting to see the propagation from the right to left. Okay, at some point, the propagation, the heat release rate already increasing because of multiple modules getting involved, and also because of preheating. You will see when the cells getting involved in this region and this region, there's a significant speed up, about 2 to 3 times speed up of propagation rate, so leading to a sharp increasing of heat release rate, as I mentioned before. Okay, I'm going to quickly skip this. This is just a temperature, the time of the thermal runaway initiation of each array, pretty much reflecting what I just explained before. You can see for the module of origin, the propagation is really linear and steady state. The speed up is only moderate. And also even for the front propagation due to the flame is also with a similar propagation rate. The time for propagation is around 300 for each module. However, for other modules, you can see significant difference. You can see the curve starting to bending, especially at the middle part, as I mentioned, that showing the speed up of the propagation. And also you can see the time, delta t, between the propagation kind of reduce in the middle part to about twice of the speed or even 1/3 of the speed. Okay. One interesting thing I want to show is the heat release rate is really being driven by thermal runaway propagation. You can see here the heat release rate really small because only the module of origin getting a steady state propagation. Okay, here you're starting to have a much higher acceleration because of other modules starting to getting involved. So heat release rate increasing. And in this region, you can see a little bit of a drop because of module of origin burned out. And also here you have a drop because the other module burned out. However, this acceleration is really because of preheating effect by the big flame. So the cell-to-cell propagation is also speed up significantly. Okay. One interesting to point out, you can see is the module number 4 and number 5 actually initiated earlier than module number 3, which is immediately above the module of origin, is actually because of flame dynamics. You can see the flame shape of the wall fire. At the base of the fire, it's actually the fire thickness is thinner. The radiation feedback back to the module is smaller. However, with the elevation increasing, you actually have a bigger flame thickness and a higher heat transfer rate, leading to a quicker initiation. Okay. So just conclude, our problem is really the rack level, system level, stationary system. We want to understand the fire size, propagation rate, and and hazard, how to control the hazard. So we actually developed a multi-scale experiment to understand the physics and to understand the heat transfer, fire dynamics. Okay, and we built a CFD model trying to couple the fire dynamics and also capture the key heat transfer phenomena within the module, including plastic, casing, and between the module and within the rack. And our goal is really to predict the hazard in the system level. In this talk, we provide example for pouch cells. However, similar work is ongoing for different form factor, cylindrical cells and prismatic cells. All right. This concludes my presentation. I want to thank the team, my colleagues, Dongzheng, Gangxiong, and Daniel Mohandes, who is doing modeling, and also 2 postdocs working with us, Lauren Gania and Wang Krias. And also this whole research is funded by FM, Battery Safety Strategic Research Program. We thank our management team for financial support, and also our technicians and engineers in the research campus and node office for conducting all different scale of experiments. Thank you very much.
Thank you, Yuan. So I see some people have already raised some question and more is coming. So I'll save this question after Xuning's talk. So next, we will invite our second speaker, is Professor Feng Xuning from Tsinghua University. And Professor Feng is associate professor in the School of Vehicle Mobility of Tsinghua University. He is one of the leading scientists in the battery safety research, and he has established comprehensive calorimetry methods for characterizing the reaction sequence of battery thermal runaway failure mechanism, especially the anode-driven reaction zone model. And based on the proposed mechanism, he has also proposed the anti-failure strategy, including many different strategies. and he's very active in the battery safety research area. I think he is one of the most cited researcher in this area. He has so far published almost 200 papers and almost 100 patents granted. So let's welcome our second speaker, Professor Xuning.
Yes, thank you, Xinyan. So, the sharing is good?
I haven't. Yes, it's coming.
That's good. Yeah. Okay. Thank you, Xinyan, for inviting me here. I'm Xuning Feng from Huang University, from the School of Vehicle Mobility. Previously, we were doing internal combustion engine research, but when I was selecting PhD program, my mentor, Professor Wang, said that you should do something about batteries. So that is something about me. So I'm very happy to share something about our research progress on the lithium battery and the lithium-ion battery thermal failure. Yes. So as you might see that the China's new energy vehicle sales is about 20 million, and the fire accident last year is 2,000. So it's very easy to calculate the failure rates. It's 1/10,000 vehicle and 1/1 million cell. And the battery safety started to threaten applications in vehicle, power grid, and ship and aircraft because the lithium batteries are using in many scenarios. So this is the market of lithium-ion batteries. So from first the invention of lithium battery, and then to the 3C commercial electronics like laptop and smartphones, and then go to electric vehicles, and Tesla and BYD and also some car manufacturers in China lead this industry. And then we are considering using the lithium phosphate into large-scale energy storage. It's a brief introduce. And you could see that the cost of lithium battery goes down very fast, from 5 RMB per watt hour and to 0.6. Beyond the lithium battery, we are trying to make many underwater and electric aircraft, and also electric vehicle wants some higher and higher energy density. And now we are making a safety balance, using NCM batteries or LFP batteries. But however, the energy density and the size of the batteries are going up and up. This is our our view about the beyond the lithium batteries. You could see, as the cycle life and the energy density going up and up, and we may have four technical roles. First one for lithium metal, and the second one for the all solid state batteries. And for NCM, it's going to be compromised with the safety and the energy density. And for lithium phosphate, it has a low cost roadmap. It's like a very long cycle life, but not a very high energy density. This is what for energy density. Yes, and I'm not sure. So it seems that the GIF do not work, but you could see that from the lithium phosphate, this is lithium phosphate. You could see for the LFP batteries, it's during similar way, it's a vapor and gas. It work with vapor and gas. For the jet fire and the electric vehicle, you could see the NCM batteries goes into jet fire. However, the lithium batteries going to do metal explosion. I'm not sure whether why this can. Yeah, this works. Okay, now it works. Yes, the GIF works. Because you could see that the metal explosion just occurs very spontaneously in a very short time. It means that as the energy density increases and the thermal failure becomes more and more severe. And I think more and more fire and combustion research, and I think more and more are interested in it, because you could see that from no fire to jet fire to explosion, and this is quite interesting. But my background is electrochemistry, and I'm not working very in depth on the fire research. So this is our many interesting scientific problems about the lithium battery failure, but they sometimes could put together. But I think most of them independent exist. First, you could see the short circuit. It's a kind of electrochemical thing. For the cathode and anode, the lithium battery, the cathode is oxidant. like NCM, LFP always has oxygen inside. And for the anode, it's a lithium intercalated into the graphite or silicon, or using lithium metal. So I regard it as a reaction vessel, like what we are doing some combustion research. You make some methane and oxygen together, and this reaction vessel is very small. It's only 10 micrometer, because the cathode and anode are separated by a 10 micrometer thickness separator. And what makes this hazard more severe is that it's filled with carbonate. It is filled with flammable carbonate. Yes, and the short circuit is quite easy to happen, and the failure rate caused by short circuit means that 1 in 1 million cell would have a short circuit between the cathode and anode, because the distance is very small. If the cathode and anode trigger the chemical reactions, you could see what Donald Finnegan and Paul Shearing published in 2017. This is made by the European synchrotron. You could see within maybe milliseconds, the reaction occurs, and this means when 1000 degrees Celsius temperature rise, and you could see this is the 18650 reaction layers. The reaction is very fierce, and what we see outside the batteries is a little bit different from the inside the reaction, because inside we do not have flame, but outside you could see gas venting and triggers jet fire. And what I'm doing in my PhD program and also keep working is what Dr. Wang said, that heat transfer propagation from one cell to another, and this makes the case more harder to manipulate, because one cell have reactions and flame, but many cells have this propagation. Is very hard to do fire extinguishing. I'm trying to do some work on the basic scientific principles, because many researchers has a very good test facilities. But for the universities, we are trying to find some relationship between some experiences, and trying to find some equations to describe, like a short circuit, thermal runaway, fire propagation, and also I'm thinking about why the lithium metal battery would have an explosion, and also all solid state batteries are going to show some explosion behavior. So first, let me introduce something about thermal runaway and fire. This is our view about thermal runaway and fire. So thermal runaway is a reaction inside, and the fire is jet fire outside. And this is a brief history of battery thermal runaway research. And the first definition of battery thermal runaway from the Royal Academy of Aeronautics, and this is Earwicker, said that in some conference for the nickel chromium batteries failure. And afterwards, Sandia and also NASA, they have some researchers using the Simonov series. And Dr. Wang and also Professor Sun Jinhua, they make the more clear definition about thermal runaway using the Simonov theory. Our research starts from 2012, funded by BMW, studied the battery safety problem when I was a PhD student. This is what we get from accelerating rate calorimetry test. This test has a very good repeatability, so could see that all kinds of batteries have these three characteristic temperatures: T1, T2, and T3. So T1 is the loss of the thermal stability, and T2 is the triggering of this thermal runaway. And after T2, the temperature rises very steep and goes to T3. This is the maximum temperature during thermal runaway. So what are the underlying formation mechanisms for the T1, T2, T3? We have worked for another 5 years, and you could see from this is the DSC peak. There's a differential scanning calorimetry peak, and this has an underlying mass mechanism that can help us to interpret why we have reactions there. And this is what we conclude from NCM batteries. It's, we call it the 10 reactions for battery thermal runaway. So from T1 to T2, and here we see that this is the interface. This is the cathode interface and anode interface. They are going to fail and release some oxygen and also reductive gases. And near T2 are from T2 to T3. That's T3 for lithium metal or NCM 9 series is up to 1,500 degrees Celsius, and the major heat release are between the cathode and anode, but not directly contact between cathode and anode. Although I have a separator between them, but the oxygen is released from the cathode, and the reductive gases, I mean the carbonate, are reducted as the lithium interface at high temperature, approximately 1,180 degrees Celsius, and then it release some reductive gases here. This makes the major heat release. So if we see this kind of reaction, we show this is the reaction vessel, and it has a reaction zone for anode, a reaction zone for the cathode, and the reaction zone for between the cathode and anode. And the reductive gases and oxygen meet as the zone B, and then it went out from the battery cell. This can help us to explain why the battery can self-ignited. So the venting gas, the reactive gases, the flammable gases venting out has a temperature. This temperature is T3. If the T3 is higher than the flammable boundary, and it will ignite the battery venting gas. And the venting gas is a mixture of hydrogen, carbon monoxide, carbon dioxide, and some C1 to C3 carbohydrate. So the lowest flammable limit can be calculated, and we have a flammable boundary here. You could see that the LFP battery is located as the non-flammable, I mean the safe region. But for the NCM series, it's located at the right side, and this helps to explain so why the battery can be self-ignited. So why NCM batteries are more dangerous. And also this battery we expected has a sulfur-based solid electrolyte. It's H2S. We expect it to be safer, but actually it does not if they use lithium anode. So this week, this what we are our published paper called it the trade-off relationship between battery thermal runaway and fire. So inside the maximum temperature inside, so NCM batteries has a maximum higher temperature than lithium phosphate because the cathode of the NCM batteries, I mean the reaction inside is stronger. But for the lithium phosphate, because the reaction inside the battery is weaker, so the carbonate has more chances to be ignited outside. So the flammable gases, I mean the self-ignition temperature, and also the lowest limit of flammable gases is maybe more severe for lithium phosphate batteries. You could see the self-ignition, and also the laminar flame speed for LFP batteries is more dangerous than NCM cells. This is what we do by using the cell residues after thermal runaway to show something about the element flow. It can help us to predict the heat and gas release. There might be one coincidence for the venting gas prediction, because the ethylene carbonate has a more value about 88. So the electrolyte drilling into lithium phosphate, the lithium-ion battery is 4 grams per ampere hour. So for the molar volume gas is 22. So 88 for 22. This is like an equation. I mean equality here. So the vent gas can be predicted as what we have, how many carbon here. So for the lithium phosphate is the venting gas liter per ampere hour should be less than 1. For NCM cells, it's going to reach 3. So higher energy density cells going to be like all the 3 C's are going to paralyze into small venting gases. And also, this kind of element flow helps us to show. So from the initial time to the final time, we can doing some thermodynamic calculations. This way make some collaborations with the BMW team. You could see if the initial are the electrochemical reactions, and for the final things is the thermochemical reactions. We can calculate the energy and enthalpy released during the thermal runaway, and the arrow is very small. Next, something about the internal short circuit. Internal short circuit triggers this very large scale of ESS fire. So for the internal short circuit, we have an analogy that the internal short circuit of battery is like a detonator of TNT. Yes, I think this is exactly right. But internal short circuit is not a sufficient condition for thermal runaway, because the internal short circuit caused by the different contactness between the cathode, anode, and current collector. Only the aluminum collector, when it contact with the anode, will trigger thermal runaway. So 4 types of internal short circuit, only one triggers thermal runaway. And for the thermal runaway, it's not a necessary condition for internal short circuit, because even if there is no internal short circuit, like TNT, if you do not using the detonator, use other things to make a high temperature, it can trigger this thermal runaway. And we do some electrochemical thermocoupled failure model, try to calibrate how much heat is released during internal short circuit, and also for the thermochemical reactions. This is our results. That the energy release total for internal short circuit is only 1 to 10%. This is reasonable, like a detonator. That triggers battery thermal runaway. Next, tell something about thermal runaway propagation. This is what Dr. Wang has showed us. It's for the because for the ES system, it may have millions and even billions of battery cells inside. But the failure rate calculation is very simple here. So during the full life cycle usage, the sum of the failure is inevitable. So we have to do some fail-safe design for the large-scale ESS. This is what we call it the propagation patterns during the propagation test. I think Dr. Wang also showed some similar data here. So first we call it ordered propagation from 1, 2, 3, 4, 5, 6. It's like occurs sequentially the thermal runaway along the heat transfer path. This is easy to control, but we also show some disordered propagation. This is called by smoke migration or particle migration, or some arc generated far end at the module, and this might ignite some disordered thermal runaway propagation. And then we have a synchronous thermal runaway propagation, because inside your battery system, inside your box, the temperature is very high, and then next module may have this kind of synchronous thermal runaway propagation. This is 3 patterns of thermal runaway propagation, what in our view. And we calculate some of the energy release and also for the fire extinguishing. Actually, the water spray can only fight with the ordered propagation. During the disordered propagation, the water spray is very hard to fight with the disorder. So we have to make a no thermal propagation, or control the thermal propagation within the ordered phase. This is what we make a very simple heat transfer pair from cell 1 to cell 2 is for ordered thermal propagation model. This is some balance equations for the heat transfer. We could see that if we want the temperature at the cell 2 is cell 2 TC always lower than T2. This means that the thermal propagation triggering, and we could find this thermal propagation inhibition criterion. This criterion has 3 terms. These 3 terms are independent, so we could do some insulator design for the thermal insulation, for the using the aerogel, and also use phase change materials to fill it inside the cores. And we need the heat dissipation with some aluminum foil to make heat dissipation. So that means that how we do some design for the thermal insulators to make the first cell, the thermal runaway T3, to be less to let the second cell to be the temperature less than T2. Next, talk you something about our new findings about thermal runaway front. This is also some in situ observation from ESRF and also Paul Sharon's group. You could see from the video, we could see some thermal front. It's quite like the the flame front, but this kind of front is not gasified. It's a solid reaction front, and also the front propagates with a propagation speed we call the VTR. It's a speed of thermal runaway. This is what we do in Tsinghua University using high-speed camera to do some in situ observation of thermal propagation. This is the propagation from the anode side. This is from the cathode side. This is the magnetic coil to trigger this kind of thermal front. Obviously, you could see the thermal front propagation. I've showed Xinyan about this, and he said that this might be the microgravity, like a microgravity combustion there. And actually, the thermal front is not ideal. But if we make ideal thermal propagation calculation, you could see that the speed of the solid speed of thermal front is quite like what we have for the flame front. Also, it is in proportion of the 1/2 order of heat transfer, and also C is for the reaction rate. And next, we are doing some nitrogen cooling, because we start the thermal front, and then we do nitrogen cooling at the far end of the battery electrode, and then we can freeze the thermal propagation in space. And after we freeze the thermal front in space, and we could show more and more chemical reactions and also the reaction information at a space level. This we're trying to use the thermal front to do some predictions about fire explosion. The solid thermal propagation generates more gases, so there might be not only one speed of propagation, one speed for solid reaction, one speed for gas migration. If the gas migrates very faster than Mach number, it make explosion. A brief summary about this. This is our current quantitative knowledge about safety task. Not mature, but sometimes still need more research. And this is what we are going to do some countermeasures about battery thermal. We call it intrinsic safety, active safety, and passive safety technologies. We do thank our team has maybe 30 to 40 workers, and we have thank for our founders. Thank you.
Thank you, Xuning. I think we are now entering the Q&A sessions, and there are 10 questions so far in the list. Let me start one by one from the beginning. I think the first two questions is for Dr. Wang, and it asks why don't you change the battery material if lithium-ion battery is not fire safe? And same person also asked the second question is does EV has a BMS system?
For second one, I'm sure EV have its own BMS system, but I'm just not an expert on that, so I won't comment too much. For the first question, it's very interesting, you know. A lot of times there's a lot of other reasons to drive, you know, the technology and energy storage. I think as Xuning showed, the cost of lithium-ion battery have been reduced. It's very economically viable, and energy density is high. The cycle, you know, all those stuff have been improved. So safety, although safety is one of the concerns, but it cannot stop the advancement of the technology. You know, as an insurance company, we do need to adapt to what's, you know, going on in the industry, and just to find the appropriate risk mitigation and risk selection tool for us. Eventually, I do think the safety portion of lithium-ion battery will improve, and has already been improved. And
maybe I'll expand the discussion a little bit. So yeah, everyone think the lithium battery is a fire risk, but as a fire researcher myself, I think compared to the gasoline, battery is actually quite safe, fire safe. But people are not worried about the gasoline, but they are worried about the safety of the battery. So what is kind of the mindset behind that? Or Yuan?
Oh, it's really, I think for gasoline, we understand much better how to contain it, how to prevent and how to mitigate the it's just because we have been dealing with gasoline for a long time. We know the risk, we know how to handle it, and a lot of the worry is coming from lack of knowledge. And I think we are gaining more knowledge on it. However, as indicated before, the lithium-ion battery is just not one kind of fuel. It's behave differently with different chemistry. When you're changing cathode, when you're changing, increasing energy density, when you're changing different, electrolyte, everything changes. There's a whole bunch of fuel. You cannot generalize to say, hey, lithium-ion battery is safe or not. Each battery have a different characteristic and evolving very fast. So we do need to increasing the research and understanding the battery safety better, so we can be better prepared for the technology evolution.
Okay, follow-up question from it's about the modeling part. Someone asked you how to simulate the gap between the battery cells, maybe some contact resistance, or maybe it's just air in between.
Oh, that's actually very interesting. Sometimes there's a gap, sometimes there's a plastic, sometimes there's like a foam. There's a different design in the module. I think sometimes the heat transfer model need to be specific to the module design and also form factor of the battery. For a specific Porsche battery, I think the heat transfer direction is one-dimensional. And at the beginning, there's a gap. The heat transfer is between radiation and convection. It could be approximated as effective conduction with certain thermal resistance. However, after thermal runaway incurs, usually there's a big expansion of the cell. So there's a gap will be, the air gap will be actually filled. There's no gap, the thermal conductivity and the resistance will be reduced. And also, if there's a plastic in between, after plastic melting, the heat transfer will be different. So we typically deal with that with effective conduction with a change of thermal resistance.
Thank you. Maybe I'll start from the last question and ask Xuning first. So how to recognize which part of one battery will jet or explode? Someone asked.
This is for prediction or modeling for.
I guess they ask whether it will generate a jet flame or it will cause explosion. How do you predict that?
So based on my knowledge for that, I mean, for jet fire, so for all kinds of batteries, if you heat it and the electrolyte will boil, so every battery will have a venting gas. But actually, if your venting gas is very hot, and it will self-ignite. This is for whether it has a jet fire, because the thermal reaction has a high temperature, and the jet will be jet flame, not only a venting gas. And if for the explosion part, I do not make it very clear. I'm still doing some research on. I'm doing some experience trying to calculate something. But my belief is that if the speed of propagation is higher than Mach number, like what we do for explosive things, is higher than Mach number, is the solid explosive things, and it will cause the explosion. But this only occurs for the lithium metal batteries. I do not hear from the lithium phosphate batteries.
Yeah, maybe I'll ask a follow-up question on the explosion, because to our understanding, explosion is a physical process. Anything with a very rapid increase of volume should be considered as explosion. It does not necessarily to require something exceed the sound speed. So, for example, a balloon have some gas inside. If you just ping it, it will explode. But I don't think anything exceeding sound speed there. So why
And also for the submarine front inside a long battery, submarine front inside long battery, it looks like a piston to push the push reaction to work and run. If the running speed higher than Mach number, it will trigger submarine away. Will trigger explosion.
So the
This
Mach number of the solid phase or the Mach number of the gas phase?
Gas phase, because during your propagation of solid phase, also you are generating more and more gases, and the gas speed is higher, is faster than the solid phase.
Okay, yes. So let me ask another one. So, yeah, let me start from the beginning because people asking. So for E1, so someone is interested in the increasing curve of module 2, which you mentioned show a linear increase. How do you think the linear increase, the slope in application? I don't know exactly what that means. So I guess here
Okay.
linear increase of the temperature.
Yeah. The propagation, the propagation rate is relatively linear. It's a steady state propagation at the beginning. I think it's Xuning also mentioned in one of the propagation, I think, what do we call one of the scheme. At the early stage, the heat conduction is only limited to his neighbor cell, and the preheating rate is quite steady because the effect of the fire, effect of the enclosure has not kicked in yet. It's almost like laminar flame propagation in a premix flame. The velocity will be laminar burning velocity. The propagation velocity is determined by the all heat transfer parameters and heat generation parameters, and the ignition delay of each cells, this parameter. So we actually developed a theory for the initial propagation without external preheating. A lot of times it's the behavior is similar as a premix flame propagation. But eventually, all the heating will compounding. You can think of in a compartment fire. Eventually, the effect of the enclosure will kick in because of the heating all the battery up to a certain temperature. Then all the battery will starting to simultaneously burning or have a very accelerated propagation. So that will trigger another level of hazard. I think Xuning also mentioned that. I'm not so sure I answered that question.
Yeah, I'm not sure about the increases in temperature or propagation speed he mentioned, but I think many studies have shown eventually it will accelerate when you have a flame or increase the temperature. And follow-up question for Yuan, how is the cell temperature inside the module you measured in the experiment? Oh, he has 5 questions. Let me see which one is more relevant. I think he asked a lot about the simulation part. What solver in FM use in the simulation to simulate the cell module and the rack level? And is it commercial code or open source code?
Oh, we build we have a fire model software called Feng that build internally at FM based on OpenFOAM. So the majority of the code is released open source. The battery module is still under development. It's not fully coupled yet. We are working on to build battery as a part of the solid phase behavior and pyrolysis model. However, the heat transfer, between the battery, the solid phase is very complex because of the involvement of other plastic and the casing and arrangement of array. You cannot deal with solid phase and one-dimensional heat transfer anymore. So the development, we already gone to some level of validation only on a solid phase. looking at the temperature of single cell and temperature of a multiple cell. We are working on how to couple with the casing and plastic and really couple with fire. So eventually it's going to be within fire foam.
And so how do you handle different scales from cell to module, maybe to stack in the simulation?
The cell level is actually in the pyrolysis part, is similar at how we treat wood or plastic. The self-heating, the heat transfer, and also the heat generation and the generating of a combustible gas is in pyrolysis solid phase, and coupled with gas phase solver of fire foam.
I
And
see.
fire foam will handle all the heat transfer between the flame back to the solid phase. And also fire foam also handle the internal heat transfer between the cells in the solid phase. But the heat transfer will be just more complex and three-dimensional and need some engineering simplification because of the first principle, like meshing and the heat transfer is overly too complex for large-scale industrial application. So.
Okay, I think that also answers the another two questions about the model. So I'll switch to Xuning. Someone asked you about the 10-step reactions, and how do you determine and calibrate these kinetic parameters for these reactions? And how are these reactions used to predict the thermal runaway propagation?
Yes. First thing, so using Kissinger method, using differential scanning calorimetry by different scanning rate, and then using the Kissinger equation, you could got the kinetic parameters. And actually, this year we published one paper in Joule. So now we're using AI how to facilitate the kinetic parameter calibration. And also the 10-step mechanism improved the thermal prediction. You could see that not for all kinds of cells will have a 10-step reaction mechanism. Sometimes it only maybe have one, or maybe have a 6, maybe have 5. But actually, all cells may have this kind of 10 reactions. Depends on different cell chemistries. And also, the 10 reactions and the major heat release is between the cathode and anode. If you are only want to doing thermal modeling for thermal propagation, you do not need to simulate 10 reactions. Only the reaction between cathode and anode is okay for your predict thermal propagation, because other reactions the heat is very tiny.
So maybe I'll follow up. So you mentioned the Kissinger's method is used to analyze the thermal gravity data. Is that correct?
Not thermal gravity, the differential scanning, the temperature and the heat flow data.
The DSC data.
Yes, data, yes.
Okay, and as you're talking about 10 steps, some steps may not be so important. Do you think you can further simplify it into maybe a 5-step or 3-step kinetics?
Yeah, now we are working with ANSYS to make an N step. So this is customized. So any steps you want. If you want 3 steps, because for one cell, sometimes someone thinks that is 3 step, someone thinks that's 5 step. But I mean, it depends. But it's free, not just very stringent to make maybe some numbers of that.
I see. Maybe for the initial process, some reactions are important. Maybe for the propagation, some others are more important. Also depending on the
Yes,
process.
as long as the target is accurate.
I see. Okay, there's one question for both of you guys. They ask the repeatability of the experiment. Is that good or not? And how to handle if the experiment result has poor repeatability? Maybe Yuan first.
Okay. For the cell level, we have done research to conduct a 10 repeat experiment. Then we look at the distribution of energy release, distribution of temperature and energy distribution internally in ejectile. There is some level of uncertainty, as expected. However, actually the standard deviation is actually smaller compared to different chemistry and different battery type. So basically, there's a clearly, for example, LCO battery is more dangerous than NMC is more dangerous than LFP. So it's actually there's certain level of repeatability of differentiating, global level of hazard, but there's some level of variability. We can, basically, how do I say, to introducing some stochastic variability in our model to capture some variability, but however, we haven't found it very necessary at this point because there's a lot of other uncertainty, and also when we're looking at small scale to large scale propagation, there's a lot of other effects. We are not zooming in to look at the small details. We're looking to say, hey, do we capture the bigger physics? And also in going to the larger scale module level, we have not done repeat test for rack level, but we done repeat test for module level. A lot of key physics that I mentioned is very repeatable, actually. With a lot of small variations you can understand, but you have to zoom out a little bit looking at the bigger signals.
Xuning, what about your experiment? Is the repeatability good enough?
That's a very good question because it reminds my early years for doing thermal research. So first time I'm using the penetration test, something like the overcharge test, and the repeatability very poor and very hard to write some papers or make some analysis or to make some models. It's very hard. That is why I using ARC. So why I'm using ARC because it's adiabatic environment. So the test repeatability is much higher. And also inside ARC, because you do not have you have limited oxygen, so no fire inside, only the chemical reaction inside. And the only thing you have to do for some randomness is to calibrate or trying to calculate something about the venting gas. Yes.
Thanks.
And
Okay.
yes, for propagation, I recommend you if you want to make some repeatabilities, more higher repeatability. So order propagation is okay, not for the disorder or synchronous, because for the disorder sometimes the jet fire and the jet particles or the jet electrolyte may set at different places inside your module. This is very hard to predict. Yeah, here that Xinyan you are trying to simulate the Nanjing building's fire, so it's very hard. They have some newspapers everywhere, so it's very hard.
Yes, to reproduce a building fire is also very challenging. Another question for Xuning. Someone asked if the ARC data can be used to identify the larger scale module safety. I think that's what it means.
Actually, we do not put a module inside ARC. But although we are putting maybe 1,000 ampere hour lithium phosphate battery inside ARC. Because its working principle for the ARC is only have one temperature here and one temperature here. This is for battery sample. This is your calorimeter. It follows they together. But you are using battery module is very hard to follow many cells thermal propagation. So I do not recommend you put a module inside an ARC. But actually we are putting 1,000 ampere hour or 2,000 ampere hour inside ARC. This is okay because only one cell there.
I think what he asked is whether the ARC data can used to quantify the safety of larger scale battery packs.
Yes, because we have maybe I have shown some thermal front, the speed of thermal front, and inside the parameters inside that the lambda, the C, and also the T1, T2, T3 are also all measured by the ARC data.
Thank you. Another question is explosive speed in the laboratory. How to stop the how to stop the thermal runaway propagation? Actually, my student. Okay. Yeah. What's your opinion? What measures can be done to stop or slow down the thermal runaway propagation?
For
Yeah.
Heat insulation, and also put phase change material. I have mentioned some of that.
So the heat transfer phase change material is also useful in real practice.
Yes,
That's
yes.
what. Okay.
We are putting it into energy storage station, and also for electric vehicle. Much better than the aerogel insulator.
Oh, I see. Because phase change material is not just an insulator; it's more like a cooling thing.
Yes, the keep the temperature as the cooling phase, make a high temperature gradient for heat transfer and heat dissipation.
Okay,
Very
let me.
quick.
Okay. Oh, some other questions. Why some kind of cooling system? So someone asked, is a BMS system can be designed to also control the thermal runway for Xuning?
Actually, I do not mention in this paper. So we have found that if you discharge by a very small current, it can help to quench thermal propagation. It cannot quench thermal runaway, but can quench thermal runaway propagation.
By release some.
By low temperature discharge. The mechanism is quite simple. You think that the reaction between the anode and the electrolyte, the electrons are going outside from the lithium to the electrolyte. This is the electrons the direction. If we make discharge not very fast discharge, just to compatible with this speed, and you make discharge this side, the electron is moving this side. So discharge is good, helping us to suppress the thermal runaway propagation.
Compared to do nothing. So discharge is
Yeah, compared to nothing, and also it helps us to going down, reduce the SOC of the full battery module, full battery pack. Even if you cannot suppress the thermal runaway propagation in cell 1, cell 2, or cell 3, it can help you to suppress cell 4.
Okay, let me see some other questions. Is there some way to prevent the secondary ignition after thermal runaway? When basically talk about reignition, can we prevent the reignition of the battery fire? For both of you guys, I think maybe this one is from fire service department, because sometimes we put out the battery fire, it really start again. Is there some way we can prevent this kind of reignition?
In my opinion, it's going to be quite difficult to 100% prevent, because there is some build condition already, and sometimes heat transfer is just slower, so it just didn't get into the battery will be triggered somewhere along the way again. It just need to if one incident happens, if it stopped, the best way I think is to isolate the battery who had gone to failure, and also watching. It's almost like a fire watch. You could always have reignition. You put out a fire, you need to until it's all cooled down and watch the reignition. I don't know what's make them to other than cooling down and waiting for cooling down. Yeah, the reignition can happen.
Okay, I think some related question is also how to stop the thermal runaway and how to stop the thermal runaway propagation. What's the difference there?
I mean, stop thermal runaway propagation is really one kind of a passive protection. You either have an active protection, spray water, coolant, suppressant, whatever, or passive design, you put in some insulation, and so that when one cell getting somewhere away, it do not trigger other neighboring cell or putting phase change material, all those design. And another thing is you have a different level of passive protection. You could potentially to say, hey, if I have one cell somewhere on the way, how do I design inside the module to prevent propagation to other cells? Or you could say, hey, I cannot prevent propagation within the module. Can I do something between module, putting a larger space, have certain cooling between the module, and also put out the gas phase fire, which accelerating the heat transfer between cell, and those mechanisms need to be designed in a different level. And also, as an insurance company, we also do a lot of work for separation distance between BES as a container. Each container is very big. When you have a fire, pretty much the whole container is gone. We want to making sure the flame from one container burning do not spread to another one, and the separation distance and some heat insulation design is important. But the passive protection need to be done in different levels.
Anything to add, Xuning?
Mm.
Yeah, to my understanding, probably there's nothing can be done to stop the thermal runaway of a cell. Maybe the liquid nitrogen can do that. Probably no other agent can stop the thermal runaway itself. So I think most work should be done to preventing the propagation of a thermal runaway rather than control the thermal runaway of the single cell itself. And follow up Iwan's question, do you have a good number for the separation distance between containers? How many meters?
Oh, we do. We have our standard we published. There's engineering calculation, but also we have a specific specific risk analysis for specific product in the market. We looking at the large scale testing data and do heat transfer and looking at all kind of insulation and design principle of the module. Then we can decide what would be the separation distance. I don't want to put in a number, right here, just to, I'm afraid of misleading. I encourage people to read our standard. And there are some product specific guideline which is not available to everybody now.
I see. So there's no magic number.
Yeah, we only do this kind of analysis when we have information from our client or from the manufacturer who provide all those details that we can do appropriate, evaluation. Yeah.
Okay, I think the last question is what's the ignition mechanism of triggering the flame, the ignition of the flame, whether it's from the hot particles or also from some other mechanism? Maybe Xuning can answer that.
There is one time our group thinks that it's hot particles. There's one time because your aluminum foil will collapse and vent out with the venting gas. It will have a temperature higher than 600 degrees Celsius. But currently we think that this is just a kind of compression ignition. You have a very high temperature and a high speed venting gas. It will self-ignition. Because the temperature for the self-ignition of venting gas, self-venting gas, is just between 500 to 600 degrees Celsius. We do some statistics about that. All kinds of lithium-ion batteries. The venting gas has a self-ignition temperature between 500 to 600 degrees Celsius. So for the NCM cells, it always has a T3, I mean Tmax higher than 600 degrees Celsius. So the self-ignition is very common.
What about the arcs? Can arcs ignite these jets? Is it important?
Yes, the arc ignites because the arc has a temperature higher than 2000 degrees Celsius. We have some measurement for that, and the arc that occurs as a pole, as a battery pole has the positive or negative anywhere there. But this kind of just like the plasma. I think you are familiar with that. Yes, plasma of the electrolyte or the air gas between them, and the temperature is very high, and this is also very hard to control because the electrolyte is poured everywhere sometimes for the lithium phosphate, especially for the very large lithium phosphate batteries. And then because the electrolyte, the pouring electrolyte is conductible. So anywhere it pushes to everywhere and anywhere there, and it will generate arc. And the ignite itself, even it is cool.
Maybe Yuan can add something, because I remember you also collected the solid particles injected from the internal of the battery.
Yeah, we collect the solid particle more for heat transfer calculation. We want to know how this ejectile, carry energy and deposit energy into neighboring cell and do the convection and the conduction, if the ejectile is solid or gas. So they have a different energy ratio, and also they have a different heat transfer mode. In terms of ignition, we had some experience. So sometimes when the reaction is quite violent, for example, LCO and NMC, there's always auto-ignition. However, it's hard to say this auto-ignition is not facilitated by the spark. So because we do see hot like particles which is still reacting, I think potentially could serve as spark ignition. For some low LFP or some different kind of LTO battery, ignition is not guaranteed. Usually self-ignition is hard. Even pilot ignition, even we putting a big flame there, sometimes we ignite, sometimes we don't. I think it's due to, again, typical ignition theory. You have your mixture, how much premix mixture you have, and if you have a diffusion flame, what's your strain rate, all those things, and where your ignition location, and all affect your ignition. However, I think the ignition study related to single cell usually is not relevant too much in practical world, because the cell is always, other than battery manufacturer storage, it's just battery factories. Typical battery is always encapsulated in the module. So in the module, what happens is the hot particle will be trapped within the module, and within the module there's no oxygen, there's no ignition. When the combustible gas exits through the module, the hot particle already being filtered out. You have hot gas, but the hot gas do not get into auto-ignition temperature a lot of times. Without external pilot, it's not that easy to ignite compared to single cell. And however, you do have ignition, in a lot of practical scenario like electrical arc, a lot of other hot surface could serving as a facilitator of ignition. So it could be a complicated phenomenon.
Great. I think we have a very detailed discussion, and it's already 1.5 hours. And it's a good time to stop today's webinar. Let's thank our two speakers again, Professor Xuning, Feng, and Dr. Yuan. And I think the next few days there will be another webinar series on another topic. So I encourage all the attendees to join the other webinar in future. Thank you. That's all for today. Good night. Good morning.
Thank you. Bye-bye.